Alcohols are classified into primary, secondary, and tertiary. To locate a primary alcohol, always look at the carbon that is connected to the OH and see how many carbons it is connected to. So if it's 1, then it's primary. If it's 2 carbons, then it is secondary. And if it's a 3, it is tertiary. Normally, for the reactivity of the alcohols, the tertiary alcohol is the most reactive because this carbon over here will be the most partial positive carbon. So this is why it's going to be more reactive than the secondary, than the primary alcohol. Now, alcohols, they do have a polar bond, which is the COH bond. And this polar bond is going to form a direction of polarization where the carbon will be partial positive and the oxygen will be partial negative. So in this case, the carbon here is going to be the electrophile. So if there's any nucleophile in the solution, the nucleophile is always going to attack the carbon of the alcohol. Alcohols are water soluble up to 5 carbons. Majority of alcohols are liquids. Above 5 carbons, they are water insoluble because of the long hydrocarbon chain. They have hydrogen bonding, so this is going to increase the boiling point. So if you compare an alcohol to an ether to an alkane, the alcohol is going to have the highest boiling point. With respect to the reactivity, as we mentioned, tertiary alcohols, they are way more reactive in reactions than secondary, than primary alcohol. With respect to the boiling point, the branching decreases the boiling point. So the higher the surface area of the alcohol, the more exposed it will be, of course, within the same carbon. So here I am comparing a chain of 5 carbons for all. So this increases the boiling point. As for the alcohol nomenclature, all nomenclatures for organic compounds will be based on alkane nomenclature. So all what you need to do is simply name your alkane, drop the E in the alkane, and add an OL. You're going to choose the longest carbon chain that has the OH. No matter how many carbons is this a chain, your longest carbon chain always need to include the OH in it. And always give the OH the lowest number because alcohols have a higher priority in naming than alkanes. So this is why the parent name, the ending is going to be in an OL. So you're going to start by the OH, in this case, being on carbon number 1 in there. And this is 5. And the name is going to be pentane, but you're going to drop the E and add an OL. So it's going to be pentanol. This is the IUPAC name. Since this one is a small alcohol, we can name it as common as well. And to name it as common, it's going to be named as an alkyl alcohol. We don't go by common names much whenever we are naming alcohols. Common names are restricted to just 6 carbons. So for here, I do have a cycle, so I need to include the cyclo in my name. So this is going to be a cyclohexane, but you're going to drop the E and add an OL, so it's going to be cyclohexanol. The rule says that you cannot have 2 vowels next to each other. So when you write the hexane, hexane ends in an E, and then if you want to add the OL, these are 2 vowels in there next to each other, so you got to drop 1, so definitely you drop the E. This is common name, you name it as an alkyl alcohol. And of course, if you have 2 substituents in there that are on the same side with respect to the cycle, you name it cis. If they are on opposite sides, you name it trans. So this is going to be transformed to cyclohexane. Since you have 2 OHs, you need to use the prefix di in there in front of the OHs. Now, if you have more than 1 OH, as in this case, you have to include on what carbons the OHs are, because they can be on any carbons, especially in the cyclohexane. They can be on 1,2, they can be on 1,3, on 1,4. So this is why you have to include where your OHs are. So the 1,2 is going to indicate where each OH is going to be. Alcohols have a higher priority in nomenclature than the alkenes. So your ending is always going to be in the OL of the alcohol, and the alkene in this case will be given the second lowest number. So this is why I'm going to start numbering from this side and not from the other side, because my priority is the OH, and the OH needs to get the lowest number. So the OH is going to be on the second carbon, and the double bond starts on the third carbon. So that is going to be 3-pentan in this case. So you're going to do 3-pentan. Don't forget that we dropped the E in the pentene because we are adding the OL. Even though you have the 2 in there between the E and the O, you still drop the E. So you have to indicate where the OH is, and the OH is on the second carbon. So this 2 belongs to the OH, and that 3 is for the double bond. That along the double bond, we have stereochemistry. We have cis and we have trans. And here we do have a trans because the 2 groups that are the same, which are the hydrogens, they are on opposite sides. So this is why this is called a trans 3-pentan 2. We can also use the E and the Z system whenever we are checking the stereochemistry of the groups around the double bond. So the difference between cis and trans and E and Z. Whenever we say cis and a trans, we mean that we have 2 groups that are the same around the alkene, whether they are hydrogens in there. So if the hydrogens are on the same side, they need to be 2 groups that are the same around the alkene. So let's say if I have something like this in there, if I have 2 ethyl groups here, these are on the same side, these are the same, or 2 hydrogens are the same, then I can use the term cis around the alkene. Trans is the same thing. Whenever I have 2 groups that are the same, they have to be the same around the double bond. So here I can have an ethyl again and an ethyl again, and now based on these hydrogens that are the same, or based on the ethyl groups that are the same, they are on opposite sides, so I can use a trans. So cis and trans, this exists between double bonds, carbons of the double bonds, and these 2 carbons, they need to have 2 groups that are the same on adjacent carbons of the double bond. Now with respect to E and the Z, Z is the same thing as cis and E is the same thing as trans, but we use Z and E based on the priority, and if we have 3 or more different groups around the double bond. So again, cis and trans, you need to have 2 groups that are the same around the double bond, so that makes it 2 different groups. Z and E, if you have 3 or more different groups around the double bond. Let's have an example. So if we have something like this, if I have a double bond, on the double bond here I have an OH, I have a Cl, I have a hydrogen, and I have an ethyl. Take a look here. This is my double bond, and along the double bond, see how many groups that I have different. I have a hydrogen, I have an ethyl, I have an OH, and a Cl. So this is going to be 4 different groups over here. So in this case, if I want to set the priority, I cannot use the cis and the trans. I need to use something else for nomenclature. So to do this, we are going to go ahead and divide the bond in half, the double bond in half, and then look at each carbon separate, and now go with the priority of the groups along that carbon. So this carbon is connected to what? It's similar to whenever you were setting the priority for R and S, you went 1 atom at a time, you do exactly the same thing. So this carbon over here is connected to 1 carbon and a hydrogen. Between a carbon and the hydrogen, the carbon has the higher atomic number or mass number, meaning higher priority. So here in this case, your higher priority is going to be placed on top. So I'm just going to go ahead and put a small asterisk. This is not a chiral center, but just this is an indication that my higher priority is on this side over here. And then between an oxygen and the chlorine, so you look at just the oxygen in there, not the OH, just the oxygen and the chlorine. You move 1 atom at a time. The chlorine is a higher atomic number than the oxygen. So in this case, your higher priority is going to be on this side. So notice that your higher priorities are opposite inside. So this is why this is called the E isomer. E means the trans, but I can not use the term trans because I have 4 different groups around the double bond. Let's go ahead and consider another example. So if I have a double bond in here, and if I have a bromine, if I have an OH, if I have a methyl, and if I have an ethyl. Again, divide your double bond in half. You have to locate your double bond and divide it in half. And then look at the groups that are on the double bond. So you have an oxygen in there on this particular carbon, and you have a carbon. Between the oxygen and the oxygen has a higher priority. So I'm just going to go ahead and put a small asterisk on this side. Then go ahead and look at the other carbon that constitutes the double bond. And look at the groups that are connected to it. You have a carbon and you have a bromine, and the bromine is a higher priority than the carbon, then the small asterisk is going to be here. These two higher priorities are on the same side. So this is why this is going to be a cis. We cannot say it's a cis, so this is why we term that a Z isomer. So whenever you have a double bond, check if you can use the cis and the trans. If you cannot use the cis and the trans, then you can go ahead and use the E and the Z. 3, since I have a double bond in here, I can use 2 nomenclature systems for the double bond. Since I have 2 criteria that are satisfied, I do have 2 groups that are the same. So I can use the trans in here, and the groups that are the same, they are on opposite sides. Or I have here 1, 2, 3 groups that are different. So again, I have another criteria for the E and the Z. So I can use either the trans or the E in this case. It is E because if you take a look at the double bond, just go ahead and divide the double bond. Between hydrogen and the CH3 is higher in priority. Between the carbon and the hydrogen, the carbon is a higher priority over here. So your priorities are opposite inside. So this is going to be an E. If you want to check the E and the Z, you have to put where the E is. Here I didn't put where the E is because I only have 1 double bond. If you have 1 double bond, it's fine. You don't need to put where the E is because you are already specifying where the double bond is. It's on the 3rd carbon. But if you have more than 1 double bond, then you have to locate where the E is. Like for example, 3E. To name ethers, there are 2 types of ethers. Ethers that are symmetrical, and symmetrical ethers means that they have the same R's. And ethers that are not symmetrical, they have different R's in there. In this case, when you want to name an ether, always name it as an alkoxy, methoxy, ethoxy, and so forth. And ethers, they do not go at the end of the name. So they are not a parent name. They are named always as a substituent, as an alkoxy substituent. The ending of the name always is going to be in the alkene. Something like this. So if you have an ether, then you're going to choose the longest carbonate chain in there. So this is going to be the longest carbonate chain. Stop at this carbon. And now your OCH3 is going to be a substituent, in this case, on this carbon. Give it the lowest number, so it's going to be 1, 2, 3, and 4. And we're going to name the OCH3 as a methoxy, and then the parent name is going to be an alkane, which is a butane. This is the common name of how we do it. Same thing over here. So your longest carbonate chain is going to be 2 carbons. And on the first carbon, I do have an OCH2CH3. So this is going to be an ethoxy ethane ether. To me, common names are for smaller ethers. And to name ethers, simply you name the 2 R groups. If they are not branched, you can name those as common. So name the 2 R groups and stick the word ether at the end. This is going to be diethyl ether. Diethyl ether is an organic solvent that we use a lot in the lab. Here, always if the R's are different, this is a case of an asymmetric ether, then arrange them in alphabetical order. So you start with the butyl first, and then the methyl, and then you stick the word ether in there. This is another example. Choose your longest carbon chain, and then give your substituent the lowest number. This is a tertiary butoxy, and it is going to be an octet. To name epoxides, what you need to do is name the longest alkane chain to which the oxygen atom is attached, and then use the term epoxy to name the epoxide substituent. Something like this. So this is the epoxide here, and the epoxide is attached to these two carbons. So you name the longest alkane chain first, and the longest alkane chain is the 5 carbons in here. And then I know that my epoxide is between carbons 2 and 3. So now I'm going to name the epoxide as an epoxy alkane. The alkane is going to be the longest carbon chain. And here in this case is going to be a pentane. So it's going to, and the epoxide is between carbons 2 and 3. So it's going to be 2,3 epoxy pentane. Now, since there is a stereochemistry around the epoxide, you have to indicate that the groups are on the same side. Then this is why this is going to be a cis 2,3 epoxy pentane. Same thing over here. This is where the epoxide is, and you have a CH3 next to it. So this is a chain of 3 carbons, and the epoxide is between carbons 1 and 2. So in this case, this is going to be 1, 2. It's going to be epoxy, and it's going to have a substituent which is a methyl. So name the methyl, and then the ending is going to be propane. Here, the epoxide is between carbons 1 and 2 of the cycle. So the ending is going to be a cyclohexane, and the epoxide is on carbons 1 and 2 of the cycle. So it's going to be 1,2-epoxy cyclohexane. Since I did not indicate the stereochemistry of the epoxide, no need for you to indicate the stereochemistry of the epoxide. But normally, when the epoxide is connected to a cycle, it's going to be always cis, because the bonds are going to be in plane. You're not going to have a bond here that is behind and another bond that is in front, meaning that these two bonds can either be in front, both of them, or they can be behind both of them. This is the only right way to draw epoxides whenever epoxides are locked in a cycle. So again, the epoxide here to represent the epoxide always bonds, they have to be on the same side, either both up or both down. The last thing that we want to name is phenols. Phenols are simply benzene that are connected to OHs. So this whole thing is called a phenol group. And whenever it exists, I cannot separate the OH from the benzene, so I have to name it as a whole as a phenol. You need to always start numbering from the OH, and the OH gets always the lowest number in there. Now, whenever you are working with benzene and you have an OH as a substituent and you want to add another substituent, so we agreed that this is going to be carbon number 1. Then the other substituent can either be on carbon number 2, let's say if it says CH3 in there. Then this one, I'm going to name it as 2-methyl. And notice that now when I want to name the benzene with the OH, I name it as a phenol. So I have to name it all in one group, which is a phenol. So it's going to be a phenol in there. The moment I say phenol, this means that my OH is on carbon number 1, and here my CH3 is on the second carbon. There's another way of naming those two substituents on the benzene by using the prefixes ortho, meta, and para. Ortho is whenever you have positions 1 and 2 occupied on the benzene. Meta is whenever you have positions 1 and 3 occupied on the benzene, and para when you have positions 1 and 4 occupied on the benzene. So here, if I have two substituents, so ortho, meta, and para, I use them only whenever I have two substituents on the benzene. So only with two substituents on the benzene. So if my substituents are on carbons 1 and 2, then I can use the term ortho instead of using numbers. So now, instead of using the 2, and I know that the OH is 1, I'm going to do O, which is ortho, and then you're going to continue the name as methyl phenol. In this case, I know that my OH is going to be on carbon number 1, then definitely my methyl is going to be on the second carbon. A case for meta is whenever you have positions 1 and 3 occupied on the benzene, something like this. Okay, so in this case, if I want to name it, again, we agreed that always start numbering from the phenol. So this is going to be carbon number 3 in there. Since I do have positions 1 and 3 occupied, so I'm just going to call this a 3. I know that NO2 is called nitro. And then I'm going to name the phenol as a whole. So this is going to be phenol. So if the OH is on carbon number 1, then definitely the nitro is going to be on carbon number 3. I can name it a 3-nitrophenol, or instead of the 3, I substitute the 3 by meta, nitrophenol. 3-nitrophenol is an old way of naming. We don't use numbers whenever we have two substituents on the benzene. It's better to use the ortho, the meta, and the para. For the para, if you have your benzene, if you have your OH, and on that I have a bromine over here, then this is going to be always carbon number 1. The ending is going to be a phenol. The bromine is on carbon number 4, so this is going to be 4-bromo phenol in this case. And again, as I said, instead of using the 4, substitute that by the P, which is para, so it's going to be para-bromo phenol. Let's have these two examples over here. You're going to choose the longest carbon chain always that have the OH in it. And the longest carbon chain is going to be here. Then you're going to start numbering from the end that is closer to the OH. So we're going to start numbering from this end over here to give the OH the lowest number. 7, 8, 9, and 10. So the ending is going to be a 5 decanol. In this case, it's decane. So you drop the E and put an OL in there. And on 5, I do have my OH. So this is going to be the first thing that I'm going to add. And this is going to be at the parent name. Now, the substituents that I have are the OCH3 substituent. And I have the methyl substituent. Just arrange them in alphabetical order. This is going to be a methyl, and this is going to be a methoxy. So the methoxy is going to come first. So it's going to be a 7-methoxy, 8-methyl, 5-decanol. Let's have another example. Choose your longest carbon chain that has the OH in it. So this is going to be 1, 2, 3, 4, 5, and 6. So this is going to be 6 carbons here. If I go this way, notice that I did not go by the alkane chain only, and I did not leave the OH. So I didn't go by 1, 2, 3, 4, 5, 6, 7, and 8 carbons in there. I didn't go by that because the OH is not part of this longer chain. So going this way is going to be wrong. Let's see if I can get more than 6 carbons, including the OH. If I go this way, 1, 2, 3, 4, and 5, this is 5 carbons. If I do 1, 2, 3, 4, this is 4 carbons. So this is the only way that gives me 6 carbons. Always remember that if you go by 2 ways and both give you the same number of carbons, always choose the way that has the most number of substituents. This is always the rule. So now start numbering to give the OH the lowest number. So I'm just going to start numbering from here. This is 4, this is 5, and this is 6. So the OH is going to be on carbon number 1. And I know that my ending is going to be hexanol. Okay. I don't have to say 1 hexanol. So I'm just going to go ahead and drop the 1. On the second carbon, what do I have? I have the secabutyl. But if you are naming it as a an IUPAC name, do not use the sacubutyl unless in the instructions it says it's okay to use it, because sacubutyl is a common, it is not an IUPAC. So if I want to name it as an IUPAC name, then it's going to be 2, open the parentheses in there, and then what I have here is carbon number 1. This is carbon number 2. This is carbon number 3. So this is going to be my longer chain on carbon number 2, and then I have a methyl on 1. So that is going to be 1-methyl propyl hexanol. If I have a cycle, then always start your numbering from the OH and give that the lowest number possible. It doesn't matter if there are substituents on that carbon or not. Please start numbering from the OH. OH needs to always get the lowest number in there. And then go to the second substituent here and give it the lowest number. So naming this as an IUPAC, it's going to be a cyclopentanol. And on carbon number 1, I have a methyl. So it's going to be 1-methyl. And on carbon number 2, I have a 1-methyl ethyl. So it's going to be a 1-methyl ethyl cyclopentanol. Here, choose the longest carbon chain that has the OH. And now your benzene is going to be a substituent. So a substituent benzene, we name it as a phenol. And we give the OH the lowest number. So it's going to be 1, 2, and 3. And this is going to be 3-phenol. And it's going to be